In this section, we're going to focus on properties of logarithms. So you should have already practiced going back and forth between logs and exponents, exponentials, and logs. But we're going to focus primarily on properties of logarithms in this section so that we have some tools that we can use when we move to equations that involve logarithms. So one of the first things we need to be able to do is evaluate a logarithm on our calculator. Now, you evaluated some logarithms in the previous section, but they were kind of contrived problems to work out really nice. For example, you might have been asked to figure out what log base 3 of 9 was. And basically, you were kind of changing this into an exponential and figuring out what do I raise 3 to get 9, therefore the value of that logarithm is 2. So that's all great when you can raise 3 to something to get 9, but we're going to have a lot of problems where that's not as easy. For example, if I just change that base to 2 and ask myself, what do I raise 2 to get 9, I'm left with nothing. I don't know what that value is. So we're going to focus first on the calculator. Now, I mentioned before that there are two bases that show up more often than any other, and that's base 10 and base e. So in these first two examples, I've got an example of log of 15, and that's a base 10, and I know this because there is no subscript written there on the log, which tells me that this is a base 10. And then in example number 2, where I'm asked to evaluate the ln of 8, this is the natural logarithm, and I know that this means that my base is e. Now, because these two bases show up a lot, most calculators have both of those logarithms as a specific key on the calculator. So you can see on the right, I've got a calculator there, and this is a graphing calculator. Scientific calculators would have these keys as well. And you just have to play around with yours to figure out how yours works. Now, on a graphing calculator, if I want to do that first example and figure out the log of 15, my log key is here. And so all I have to do is hit that log key and then put in the argument of that log. Now I can close the parenthesis. When my argument is just a single term, I don't have to close that parenthesis, but it's a good habit to be in. And then when I hit my enter, there's the value of my logarithm. So the log of 15, if I round to the hundredth, is 1.18. Now, on a scientific calculator, just play around with it until you can figure out how you get that value of 1.18. On some scientific calculators, you actually put the argument in first, so you actually type the 15 and then hit your log key. So you just have to figure out how yours works. Now, on the natural log of 8, again on my calculator, I have a natural log key, and that's my ln key. So I do the same thing. I hit the natural log and then my argument, close my parenthesis, hit enter, and I know that the natural log of 8 to the nearest hundredth is 2.08. Okay, now a calculator cannot have a key for every base out there. So I want to be able to evaluate things like log base 2 of 9. So I don't have a log base 2 key on my calculator. So there is a change of base formula that I can use to evaluate the log of any base. And what it basically does is it takes any base of my logarithm and changes it into either base 10 or base e. So just know that in this formula, this is either using this formula or changing it to base 10. You basically just have to pick whichever one you like the best. I typically favor, I don't know why, there must be a reason why. At some point I decided that I favored this one. So I usually take any base that I need this formula for and turn it into the quotient of two natural logs. So the way that this works is I've got a log of any base. So in this case, in the general formula, my base is b, and my argument is a. And the way that I rewrite that as a natural log is that I take the natural log of the argument and I divide by the natural log of the base. So let's take a look at a couple of formula or examples and just make sure that we're okay with that. So in this first example, I'm asked to calculate the log base 5 of 2. So since it's not a base 10 or a base e, this is where I would need the change of base formula. So I'm going to scooch my screen over just a little bit. Okay, so I'm going to first rewrite this using that change of base formula. So the change of base formula says that I rewrite this as the natural log of the argument over the natural log of the base. So I always remember that if my argument was A and my base is B, the way that I remembered the order was just alphabetical order. So it's the natural log of A over the natural log of B. You just got to keep straight which is which. So now I'm going to go on my calculator and do this computation. So on my calculator, I'm going to hit my natural log key and then my 2. I'm going to close that parenthesis. So here closing that parenthesis is necessary because you don't want to put the division sign inside that parenthesis. And now I hit my division, natural log of 5, close the parenthesis, and there's my value for log base 5 of 2 is equal to 0.43 if we round to the nearest hundredth. So let's try number 4. And again, if you want to pause the video and give yourself a second to try it yourself, and then you can come back and see if you got it right. So on number 4, if I first change this using the change of base formula, this is going to change into the natural log of the argument, so the natural log of 17, and then I'm going to divide by the natural log of the base, so it's the natural log of 1/2. And now I just get on my calculator and do that. So I've got the natural log of 17, close the parenthesis, divided by the natural log. Now for 1/2 you could put in 0.5 if you want to, but if you've got a fraction that you don't know the decimal equivalent to, you can just type in a fraction using the division key. So now you can see on the screen it's the natural log of 17 divided by the natural log of 1/2. I hit enter and there's my value. So I've got negative 4.09 if I round to the nearest hundredth. So this is a formula that you have to remember or have handy with you when you're taking a test, so that if you run into logs that aren't natural log or aren't base 10, you know how to use that formula to evaluate the logarithm on your calculator. Okay, so let's move to those properties of logarithms. And I'm not going to need this calculator for the properties, so I'm going to go ahead and get rid of that. Okay, so we're going to move into properties of logarithms that we're going to use when we're working with equations of logarithms. And there are 3 primary properties of logarithms that we need to learn. Now remember, kind of my mantra the other day was that logarithms are exponents. So these 3 properties of logarithms are going to mimic properties that you already know about exponents. Now you do want to make sure that you learn these properties, both reading it from the left to the right and from the right to the left. So let's take a look at that first property. In the first property, if we read it from left to right, what it's basically showing me what to do or how to do is how to add two logarithms with the same base together. So to add two logarithms together, I can write it as a single logarithm with that same base, and the two arguments in those logarithms gets multiplied together for the new argument. Now, if I read this property from right to left, what it's showing me is that I can split apart an argument in a logarithm, add a multiplication symbol by writing it as the sum of two logarithms of the same base. So I mentioned that this is similar to exponential rules. So the rule in exponents that you are familiar with is what I do when I multiply two exponential factors together of the same base. When I multiply these together, the rule is you add the exponents. So looking at this property from right to left, that's exactly what we're doing. And we'll look at some examples. So I just want to talk through the properties first. Okay, in the second property, if we look at it from left to right, what it's telling me is how to subtract two logarithms that have the same base. And what I do is take the two arguments that are in those logarithms, and I create a new argument where I have the first argument divided by the second argument. And if I look at the property from right to left, it's showing me how I can split an argument in a logarithm at a division sign by writing it as the difference of two logarithms, where the numerator is my first log and the denominator is in my second log. Now, this property exponentially is what I do when I divide two, two algebraic terms of the same base. That when I divide, I subtract exponents. I would get x to the fifth. So working this property from right to left is mimicking that same property. Okay, the third property. In that third property, if we look at it from left to right, this is showing me what I can do when I have an argument that has an exponent on it. And what it tells me is I can take and move that exponent out in front of my log, giving me that as a result. Now, if I look at the property from right to left, what it's telling me is that I can take any coefficient here in front of my log and move it in as an exponent on my argument, which would end up looking like that. So the property this is mimicking with exponents is what I do when I have a base and a power, and then all of that is being raised to another power. So a power to a power, those exponents get multiplied. And so since a logarithm is an exponent, there's the multiplication of those two exponents. Okay, so let's take a look at some examples. That's where you really start getting to learn the properties. So you're going to have to use these properties in two ways. One is to rewrite the logarithms as a single logarithm. So actually perform the addition, subtraction, and pulling in of the exponent. And then also to be able to pull apart an argument as much as you can. So in this example, we're going to rewrite this as a single logarithm, and all the logarithms should have a coefficient of 1. So any numbers out in front of those logs we're going to pull in to the argument. Okay, unless I have parentheses, I want to kind of work these problems left to right. But what I'm going to start with is always any coefficients that aren't 1 or -1. -1 is okay too. So I'm going to identify any coefficients in front of my logs that can be moved into the argument. And so the property says that any coefficient out here can be moved into the argument and be placed as an exponent on the argument that's already there. So that's my first step. So that means this is going to be rewritten as the natural log of x cubed minus the natural log of y plus the natural log of z to the 1/2 power. So all I did was pull in and use that property 3 and pull in those coefficients and place them as exponents on my argument. Now I'm going to work left to right, performing the addition or subtraction. So the first thing is to subtract these two logarithms. So the rule says that when I subtract two logs, I get another single log where the argument of that log is the first argument divided by the second argument. So I've got the natural log of x cubed minus y, or divided by y, sorry, plus I still have to add that logarithm to it. So the last step is to perform this addition. So to add logarithms, I'm going to get a single log of the same base, where the argument of my log is going to be the product of the first argument and the second argument. So remember, if I multiply a fraction by something that's not written as a fraction, that's understood to be over 1. So that means that my numerator of my argument is going to be x cubed z to the 1/2 all over my denominator y. And so that's what my final answer would look like. I've got a single logarithm and the coefficient out in front of that log is 1. Okay, so let's try another one. And again, this is a good time for you to practice it first on your own and then come back and see if you get the answer right. Okay, first thing I want to do is pull in any coefficients out in front of my logarithm, but you're not going to pull in any negative coefficients. You only want to pull in the number that's in front, but leave any minus signs. We don't want to create negative exponents. So I'm going to pull my 2 in as a power on x, which is going to give me log of x squared. I'm going to pull the 3 in as a coefficient, as an exponent on y. So this is going to be minus the log of y cubed. And then this next one is okay. There's no other number besides that -1 out in front. So now that I have all of my exponents moved in, I want to now do the addition and subtraction from left to right. So if I start with the subtraction here, I'm going to write that as a single logarithm where I take my first argument divided by my second argument. So there's that one, and I still have to do another subtraction. And now I want to do that subtraction, which is going to result in a single logarithm where I take this argument and divide by that argument. So when I do that, I'm going to end up with x squared over, and since I'm dividing by this, I don't want to create an ugly argument that looks like this. So I don't want to create a complex fraction. What I want to do is think about what this would look like if you performed the division. So if I take x squared over y cubed and divide by 5, that means I'm taking x squared over y cubed and multiplying by 1/5. So if I already have an argument which is written as a fraction, and I need to divide by another number, that number is simply going to end up in the denominator that's already there. So don't create another denominator. Don't make it look ugly like this. Now, it might be better to write the 5 in front of the y, but I wanted to just do it in the same order that it appeared in the problem. So that's what my final log would look like. Okay, let's take a look at one more, and then we'll switch it around and go in the other direction. So here I have the natural log of x plus 3 times the natural log of x plus 5. And first things first, I want to take any coefficients out in front, move it in as an exponent on the argument. So that's going to give me the natural log of x plus the natural log of x plus 5 raised to the 3rd power. And I just want to add those two logs together. And to add two logs together, I take the first argument, multiply it by the second argument. So the argument of this ln is going to be x times the quantity x plus 5 cubed. So I'm just doing the brackets because I get too many parentheses in there. And you should always include parentheses around your argument unless it's a single term, so that the reader knows that all of that is the argument of your ln. I don't want to cube out x plus 5 to simplify this, so we'll just leave our argument like this. Okay, now let's move in the other direction. So now instead of combining logarithms together, we want to pull the logarithms apart. So you've got to remember where you can pull an argument apart. You can pull an argument apart at a multiplication symbol, at a division symbol, and you can pull powers out in front. Now, unless I have a power on the outside of a parenthesis in the argument, I'm going to save pulling powers out in front until last. So I'm going to look, actually the order that I would do things in is I'm going to do any division first, multiplication second, and then powers third, unless I have a power on the outside of the exponent, but we'll look at an example like that. But in general, this is the order that I want to go in. Okay, so looking at this first example, I want to look for any division, and there's no division in this one. And so the second thing to look for is multiplication. And I do have multiplication right here between the x squared and the y. So the first thing is to split this into two logarithms where x squared is one argument and y is the other argument. So remember, the property says I can split it at a multiplication symbol and write it as two separate logarithms. And because I'm splitting at a multiplication symbol, the operation I put between my two logs is addition. So they're splitting it at the multiplication symbol. Now the only thing I have left is to look for any powers on my arguments. And I do have an exponent on that argument, so that means that I can pull that power out in front of my log. So I'm going to write this as 2 times the log of x plus the log of y, and that's as much as I can split that argument apart. Okay, let's try another example. In this example, we want to again go in that same order. So the first thing I'm going to look for is any division, and there's division right there. So I want to split this into two logarithms of base 4, where my numerator is one argument and the denominator, yz squared, is my other argument. And then I just have to remember that when I split an argument at a division sign, the operation between those two logarithms is subtraction. And I lost my base over here. This was base 4. Okay, now the next thing I want to do is look for any multiplication symbols and powers. So notice in this first one here, in this first logarithm, I don't have any multiplication, but I do have a power. So I can go ahead and pull that power out in front. So that's going to make this term 3 times the log base 4 of x. Now on this second one, I do have multiplication. So I want to split that argument at that multiplication sign first. Now, because there's subtraction here, whatever I do in splitting this log up needs to go in parentheses. We've talked enough about after a minus sign, I should always use parentheses. So here's another case for that. So I'm going to split this log base 4 into 2 arguments where the first argument is y and the second argument is z squared. And this time I split at a multiplication symbol, so the operation between those is addition. And now I still have one more thing I can do, and that's move that power on the z out in front of that logarithm. And at the same time, I'm going to get rid of these parentheses by distributing this minus sign. So my final result is going to be 3 log base 4 of x minus log base 4 of y minus, when I distribute, and again, I'm going to pull the 2 out in front, so I'm going to have minus 2 log base 4 of z. So if you didn't put parentheses around here when you split at the multiplication sign, you would not have had the right operation sign here. So just be careful with the minuses. Okay, I got 2 more examples for you. So take a breath and turn the video, pause the video, and try it yourself first, and then come back and see how you did. Okay, so on this next example, notice that we have something we hadn't seen before in the previous examples, and that's an exponent on the outside of my parentheses in my argument. Now, there are 2 ways to approach this problem, but either approach requires that I work and deal with that 7 first before I do anything else to expand this logarithm. Now, the 2 approaches, it doesn't matter which one you choose, our answers are going to look the same, so it's just a personal preference. If you're focusing primarily on the properties of logarithms, then what you would do is move that power out in front of the logarithm and then go from there. That's the property we've been practicing. Now, the other approach is to actually figure out what this argument looks like if I raise x to the second to the 7th power and y to the 5th to the 7th power and actually create a new looking argument. If I did that, this would change that problem into the log of x to the 14th, because a power to a power, they get multiplied, and a y to the 35th. And then you would follow the rules we've been doing. You would split it at the multiplication and then deal with the powers. And that's a perfectly fine approach. What I'm going to do, just because we are so focused on logarithmic properties right now, I'm going to deal with this by strictly logarithmic properties. So that means that I'm going to start by pulling that 7 out in front of my log. So if I do that, I'm going to get 7 times the log of x squared y to the 5th. And now I'm going to split this at that multiplication symbol. So I'm going to write 2 separate logarithms, one with x squared as my argument and the other with y to the 5th as my argument. So I'm going to have, now I do have to remember that this 7 is going to come with me for both of those logs. So I'm going to have 7 times the log of x squared, and then 7 times the log of y to the 5th. And of course, because I split at multiplication, the operation between those two is addition. And now I'm going to take the powers that are still on my argument, move them out in front, and multiply by what's already there. So that's going to give me, when I pull the 2 out and multiply by 7, 14 times the log of x. And here, 5 times 7 would give me 35 times the log of y. And you can see back here, if we use the rules of exponents first, why our answers would end up looking the same. And it's purely up to you. I just wanted to focus on the logarithm properties because that's what we're talking about. Okay, last example. Start by looking for division. And I do have division right here, so I'm going to do that first. So I'm going to have 2 logarithms. I'm going to have the natural log of my numerator. And because I'm splitting at division, I'm going to have a minus sign, natural log of the denominator. So I've split the division. Now I want to look for multiplication and then powers. So in the next one, the next line, notice here I've got a multiplication symbol. So that means I can split this into 2 logarithms, where one argument is x and the other argument is x plus 1. Splitting at multiplication puts a plus sign between them. Now in the second term over here, I don't have any multiplication, but I do have a power that I can pull out front. So I'm going to have minus 2 natural log of x plus 5. And that is my answer. I cannot do any more. Remember, I'm only allowed to split at multiplication, division, and powers. I cannot split an argument at a plus sign, so don't think that you can split that argument up anymore. As long as my argument doesn't have any multiplication, division, or powers, then that's as much as I can do to split the logarithm up. Okay, practice these properties because these properties are going to show up when we get to equations, which is our next section. So make sure that you feel pretty comfortable moving back and forth with these properties.